Dear student, we have seen the statement of Nernst distribution law. I mean, what is the origin of this distribution law? That if you put a solute in a immiscible liquid system, solute can go into both of the solvents, depending upon its solubility in the solvents. I'm not telling that solvent goes into the or solvent dissolves in both the solvents to an equal extent. Most of the times it is to an unequal extent. But what does the law tell? That if you measure the concentration of the solute in solvent 1 as well as the solvent 2 and take the ratio, it is always a constant. For any concentration of solute solvent combinations, always you get a constant, and that constant K is called distribution constant. Fine, this is what we saw in our previous class. Now let us solve a simple problem on distribution law. So this is the question. A solid X is added to a mixture of benzene and water. Benzene and water is an example of immiscible liquid system, is it not? After shaking well and allowing to stand, 10 ml of the benzene layer was found to contain 0.13 grams, that is 130 mg of X. X is the solute here. It can be anything, solute here. And 100 ml of water layer contained 0.22 grams of X. Calculate the value of distribution coefficient or distribution constant. So what is the given data in the question? They have given you the amount of X in different volumes of benzene and water. So what is the formula of distribution law? C1 by C2. But for that, you should convert this amount given in the question into the concentration term. So how to do that? How to solve this problem? Concentration of X in benzene is 0.13 grams divided by 10 because the 10 ml of benzene. See, what is concentration? Concentration is nothing but amount in terms of usually weight or moles divided by volume. So 1.13 grams divided by 10, 0.013 grams per ml. Grams per ml is the concentration term. See, please don't use 0.13 directly into the formula and substitute. Convert into concentration first. Similarly, convert concentration of X in water into the concentration term. 0.22 grams divided by 100 ml. Since in the numerator and denominator it is the same unit, gram per ml, both the units cancel and the final answer would be 0.013 divided by 0.0022 is equal to 5.9. Please note that the distribution coefficient doesn't have any unit because it's a ratio of concentrations. So whenever you take ratios of two same quantities, you always get a number, is it not, without unit? That is what the answer is, 5.9. So these are simple problems which you get in examinations, which you can solve bit easily. Direct substitution problems. All that you should remember is the correct formula and the data you should extract from the question and put it in the correct format to fit it into your formula. Fine. Now that's fine. So we have been talking about distribution law in the simplest of the case. What is the simplest of the case? Look at the first figure. You have two solvents, A and B, immiscible, and the X is the solute. It has gone into A, it has also gone into B. Plus, please note that this X solute molecules will be always in constant exchange between the layers. The X can move up, down. So we call that there is an equilibrium reached for the distribution, basically. I mean, why this happens? Because the boundary between solvent A and B is not an impermeable boundary. Exchange can still happen between molecules. See, this is what I mean. Straightforward, I get an example which I can quote here. Maybe you have seen, you know some basics about the cells, right? At least the life sciences know in detail, but the physical science people know the basics of cells. So what is the structure of a cell? You have a plasma membrane. Inside plasma membrane, you have water, basically cytosol, cytoplasm. Outside plasma membrane is also water, that is the surrounding environment water. So the molecules keep moving from out and inside and outside. But there is an immiscible boundary which doesn't dissolve in water on either sides, in the cytoplasm or in the outside exterior. Uh, that can be taken as a, if not directly solvent system, two systems which are immiscible. Still the exchange can happen between the cell and the environment, right? The cell is not isolated from the environment. It has to take molecules from environment. It has to give molecules to the environment. But how this transport happens? This transport cannot happen in a homogeneous system. It is an heterogeneous system. Cell is an heterogeneous system basically, or cell inside an environment is an heterogeneous system. So still the transport is happening. That is one example you can relate to this phenomena. Okay, fine. Now let us, like always, what we do in science, we take with a simple examples and then try to complicate it first. Let us complicate this a bit. It has been seen that many solute molecules, when you put in the solvent, I'm not telling only the immiscible systems, any solvent molecules, they undergo some molecular changes, structural changes. Okay, let us take an example of a simple example of sodium chloride. Fine. If you put it in water, does it remain as sodium chloride? No. It becomes Na plus and it becomes Cl minus. Is it not? This is called dissociation or called ionization. Splitting, simply ionization. Similarly, you have molecules which can undergo association. This was an example of dissociation. You can also have molecules which can undergo association. For example, if you take benzoic acid and put it in benzene or even in water, two molecules of benzoic acid associate in through hydrogen bonding, very strong hydrogen bonding, and exist as dimer. Okay, so now we have two cases. A solute can dissociate in solvent or a solute can associate in solvent. Now, how does this association and dissociation have their effects on the distribution coefficient? Because the phenomena of association and dissociation happens in pure solvent also, not just in immiscible. If you take even single solvent, still association and dissociation happens. But when you take immiscible liquid systems, two immiscible liquid systems, and then put a solute, what is the simplest of the case? Solute does not undergo association or dissociation in both the liquids. That is the case of the first figure. X is X in solvent A and solvent B. But you look at the figure left, the second figure from the first figure from the lower layer, lower portion. You have X in solvent B. Look at X in solvent B. What has happened to the X in solvent B? It has got associated. NX has become XN. Next figure, what has happened to the X in solvent B? It has got dissociated. X has become two different species A and B. Okay, so in this scenario, in this situation, how to give the correction to our distribution? What is your distribution law tells? You take the concentration of X in solvent A. You take the concentration of X in solute B. Take the ratio. Very straightforward in the first example when there is no association, dissociation. But how to take the concentration of X in the solvents after association and dissociation? This is the question. Okay, therefore what we have to do is we have to give a correction to our distribution law. So how to do that correction, I'm going to tell you. So what is that we have discussed? I have just put in the points. During distribution, solute can undergo dissociation or association. But please note that to use the distribution law and to get the correct answer using the distribution law, you should take the concentration of undissociated species in the layers. Okay, so for example, here X, look at the dissociation. X in solvent A, concentration is fine, you will get directly. X in solvent B concentration would be lower than the actual X because some of the X, some portion of or some fraction of the X has got dissociated into A and B or has got converted into A and B. So to use the distribution law now, what should you do? You should take X minus how much of X is dissociated. That factor you should take. Is it not? So distribution law holds good only when you take the concentration of same species in both the layers, in both the immiscible layers. You take the same species. You should leave out the dissociated fraction of X or the associated fraction of X. You should leave out from your calculations or from your consideration and take only the undissociated form. Basically, simple here. You take only the concentration of the undissociated form in X, of X in both the layers, or you take only the concentration of unassociated X in both the layers. Okay, so now let us give this correction to the first case. What if X aggregates or associates in one of the solvents? So the picture here is solvent A and solvent B. X is aggregating in or associating in solvent B. Okay, so what are the concentrations now? In the simplest of the case, there is only two concentration terms, C1, C2. C1 is concentration of X in solvent, or Ca, Cb. Okay, Ca is concentration of X in A, Cb is concentration of X in B. But here you will get the extra concentration term. What is that extra concentration term? C3. Okay. So let us go through the derivation. C1 be the concentration of X in solvent A. C2 be the concentration, C3 be the concentration of X in solvent B. C2 be concentration of Xn in solvent B. What is that Xn? That is the newly formed associated molecule from X, the concentration of which we should not consider for our calculation of distribution law. So what is that we should do? You should minus that concentration term of C2 from C3. Whatever remains should be used for the ratio calculation. Put the formula now. C1 by C3 is equal to KD, right? That is the distribution coefficient. But how to calculate this C3? Is it not? Because the C3 also contains, with the C3 you should minus the C2 term, right? I am evaluating what is C3 now. So to do that, you take the reaction of association. Now we are coming to a chemical reaction. Till now in all our discussion in solutions, what was the first parameter we were considering? There is no interaction between the solutes. There is no interaction between the solvents. There is always a chemical unreactivity amongst all components in our mixture. But the first time we are having a chemical reaction here. So take that chemical reaction. What is that chemical reaction? NX is associating to form XN. Let us take a simple case. If it is a dimerization reaction, so what is the value of N? 2. 2X will become X2. Did you understand this? Okay. If it is a trimerization reaction, 3X becomes X3. So write the reaction and then take the equilibrium constant of that. How to write the equilibrium constant? You know, concentration of product divided by concentration of reactant is equal to the equilibrium constant. At equilibrium is equal to equilibrium constant. So concentration of X to the power of N and then divided by concentration of Xn, that is equal to Kc. Okay. Now, what is the point here? What is the concentration of X? Is nothing but C3. What is concentration of Xn? Is nothing but C2, because that is how we have defined C2. C2 is the concentration of the associated species. Take that. So your equilibrium constant can now be expressed in terms of concentrations. C3 to the power of N divided by C2. So what is that you have to do now? You just have to simply cancel that root N. Take nth root on both sides of the equation. You get C3 divided by nth root of C2 is equal to nth root of Kc. Okay. Now this is the correction factor. You are not interested in Kc value. You are interested in Kd, distribution coefficient value. So substitute this into the Kd equation. What is Kd equation or distribution coefficient equation? Simply C1 by C3. Now dividing equation 1 and 3, you get C1 divided by square root of, not square root. If it is a dimerization reaction, it is a square root, or nth root of C2 is equal to Kd divided by nth root of Kc. And now you get a bigger constant, which is called constant, distribution constant for association phenomena, that is K. This is what the modification term is. So now simply concentrations ratio is your distribution coefficient K. If you modify that, taking into account the associated portion, then it becomes C1 divided by n square nth root of C2 is equal to K. Please note that K is not direct distribution constant. It's a modified distribution constant or distribution coefficient. Okay, fine. So now let us look at this using a problem. When benzoic acid was shaken with mixtures of benzene and water at constant temperature, the following results were obtained. Don't look at the solution part now. You just look at the data part. Concentration of acid in benzene is 0.24. Concentration of acid in water is 0.015. And whenever you want to find distribution coefficient, you have to make a series of different concentrations and then find out the concentrations of solute in all series. I mean, in the entire series. For every concentration, you should get a constant K. Is it not? Do it. Apply C1 by C2 formula and find out the constants. 0.24 divided by 0.015, you get 16. And 0.55 divided by 0.022, you get 2532. It's not obeying distribution law, right? Because what simply distribution law tells, for any concentration, you should get the K value constant. But it's not happening here. Why? Why? Because why? Then we have to reason this out. Why this is not happening? Because we have benzoic acid not existing as monomer monomer benzoic acid. Rather, it has got associated in the benzene layer. Okay, the association of benzoic acid doesn't take place in the water layer. The association of benzoic acid takes place in the benzene layer. So what is that we should do? We should now apply a modified formula. What is that modified formula? Okay, C1 divided by nth root of C2. So you take 0.015. Of course, C1 divided by nth root of C2. Okay, so take okay, anyway, don't look at this problem. C1, what is C1? 0.0 is the concentration of benzene in concentration of benzoic acid in benzene is C1 divided by concentration of benzoic acid in water. Don't change benzoic acid in water. It remains same, 0.015, 0.022, 0.029. But for the concentration of benzene, benzoic acid in benzene, make it square root. Why square root? Because it becomes a dimer. So n is equal to 2 here. So if you do this, square root of 0.24, square root of 0.55, square root of 0.93, you are going to get a constant. And that is the constant Kd. Okay, fine. So that is what is important. You have now accounted for association also. What is the summary of this whole story? When you measure concentrations in different concentrations and find out K, if the constant directly C1 by C2 gives constant for the entire series for any concentration, then straightforward you can tell there is no association, dissociation. If you don't get a constant, like in this case, then you should suspect for association or dissociation. Then use the formula of association and see whether you can get a constant. If you get a constant, association has taken place. Or use the formula of dissociation and see whether you can get a constant. If you get a constant, then dissociation has taken place. So now let us go to the next case. That is, what happens when the solute undergoes dissociation? How to correct our distribution law, or what is the correction factor? Look at a picture. The X in the solvent A is undissociated, whereas X in solvent B has become ions. Maybe it has become ions or some other species of lesser molecular weight than itself. So X is equal to A plus B. Now consider that reaction. X is giving rise to A plus B in equilibrium. So how to write now? This becomes simple, like how you write equations for your kinetics. At equilibrium or at time t, after some time, and that time t is after reaching equilibrium here. Because in all the cases, you are shaking well and then allowing the mixture to stand for some time. So this is enough time for the equilibrium to be attained. So x is equal to x is giving rise to a plus b. At beginning, 0th time, entire x is only full x. But after some time, sum of the x has become a plus b. So what is that fraction of x which has become a plus b? That we call degree of dissociation. Sometimes it is also represented by alpha. Here I am representing it by small x. So at equilibrium, 1 minus x has given rise to, or let us take 1 mole of x was there in the at the time 0. After some time t, when the equilibrium is reached, out of 1 mole, x moles of x has dissociated. So if x moles of x has dissociated, how much of A is formed? X moles of A. How much of B is formed? X moles of B. So it is 1 minus x into x, giving rise to x plus x. So now, what is the concentration of x in solvent A? C1. Simple. Because x has not undergone any change in solvent A. What is the concentration of x in solvent B? It is no longer C2. C2 into 1 minus x. Because x amount of x has got dissociated. And I'm repeating this. To find out a distribution constant coefficient, you require the solute in the same form. If it is x in solvent A, it should also be x in solvent B. So out of x, you are subtracting how much of dissociated. So the remaining x is nothing but C2. Concentration of remaining x is C2 into 1 minus x. So C1 divided by C2 into 1 minus x is equal to KD. So even in this case, if you directly take the concentration of x, you don't get a constant. You should take C1 by C2 1 minus x. But here one point comes to discussion. How much is that x? Is it 1%? Is it 2%? 50%? 80% dissociation? How much is that x? That we don't know as such now. But using our distribution law, you can find out x. That is one of the applications of distribution law. Later we will see that how to find out x. Now I hope that you have understood the correction factors given to our distribution coefficient equation or Nernst distribution law in two cases. One is during association, the other is during dissociation. So this completes our discussion on the fundamentals or the basics of distribution law. How distribution law is stated, its formula, and the modification of the formula under two scenarios of dissociation and association. Now we will move on to the last aspect of distribution law. That is nothing but the applications of distribution law. In fact, in chemistry, we have a lot of applications stemming out of this distribution law. Let us look at the important few. One is determination of association. Yeah? That is what we have been talking of. What is that you have to, I told you, if dimerization takes place, n is equal to 2, small n. If trimerization takes place, n is equal to 3. But how do we know dimerization has taken place or trimerization has taken place? For that, you take the concentrations of x in both the solvents. You see, by working out the calculation backwards, for what value of n, using this formula, square root of n Ca divided by Cb is equal to K. For what value of n, you get ratio constant. Is it for n is equal to 2? Is it for n is equal to 3? Or is it for n is equal to 4? For what value of n, you are getting that formula constant. I mean that ratio constant. That will be the degree of association. That will be the degree of association. It could be 2, 3 or so on. So simply n is the number of molecules combined to form an associated molecule. So degree of association. That is what you should find out from your experiment. This is one of the applications of distribution law, right? Because now I have taken benzoic acid and put in benzene. I don't know whether it is dimerized or trimerized. How to find it out? If your calculation gives correct fit, perfect fit, matching fit for n is equal to 2, then it has dimerized. If your calculation gives constant k for n is equal to 3, then it has trimerized. For 4, it has given oligomer of 4 molecules. So on. Similarly, you can also find out the determination of dissociation, x. That's what the degree of alpha, degree of dissociation I was talking of. Use the formula, find out the x. For what value of x, you are going to get constant k. That is what you should work out in your calculation. That x will be the degree of dissociation, or simply put alpha, degree of percentage, fraction of dissociation, or degree of dissociation, such thing. Now the one more important applications, please concentrate on this. The desilverization of lead, Parkes process. Say what happens, you know, this silver, platinum, gold, these are all noble metals. People like gold, silver, platinum so much. So we don't want to overlook any source of silver, gold, and platinum. Whatever minute amount the silver, gold, platinum could be present in that source, we still want to extract it because they are so precious. Okay, the lead ore, after extraction of lead, or there is a ore of lead called argentiferous lead. So in this lead, very small amount of silver is present. We may have just like a very small amount of silver, let it go, but we don't want it. Silver is so precious compared to lead. 1 gram of silver and 1 gram of lead are, you can't, 1 kg of silver and 1 kg of lead, the price is not just comparable. Silver is so much highly priced. So when such a highly priced metal is there, let us extract it. But what's the point? How to extract this minute quantity of silver in the lead? For that, we use our distribution law principles, application of distribution law. What we do is, the lead is melted. Okay, it becomes liquid, molten lead. To this molten lead, we are going to add molten zinc. Why? Because molten zinc and molten lead, they are examples of an immiscible system. Like water and benzene, molten zinc and molten lead don't mix with each other. Okay, so this is an extreme example of liquid distribution law. Yeah, water, benzene, you can easily imagine. But the molten metals, combinations of molten metals also give you immiscible systems. One example is molten zinc and molten lead. And then you have to again do all those shaking, agitations and all, but cannot be done manually. We use special equipments would be used for this agitation. What is the solubility of silver in both the liquids? Which are the liquids under consideration? Molten lead, molten zinc. Which are the, what is the solubility of silver? It has been found that silver is 300 times more soluble in zinc at 800 degrees Celsius. So when you do the agitation process, silver goes into zinc. Okay, now what you have to do? You have to separate the zinc layer and lead layer. That is easy because they are all these both are immiscible liquids. You can just tap off the lower layer, and the lower layer is the lead here because lead has huge high density. Lower layer is the lead, so remove the lead and the remaining portion is zinc. Okay, what have we done basically? The silver which was present in lead, we have made it now go into zinc. Actually, we have not got the silver yet. Lead alli silver nalla zinc ಕಳಿಸ್ಬಿಟ್ಟಿದ್ದೀವಿ. But zinc ಇಂದ ಹೇಗೆ ತೆಗೆಯೋದು ಈಗ silver ನಾಚೆ? That is easy. Why it is easy? Because the zinc silver alloy separates out. Zinc lead alloy doesn't separate up. It is an homogeneous mass. Whereas zinc silver alloy separates out. So you collect the cakes or the separated, this is called cakes of zinc silver alloy. But still this is an alloy. How to remove zinc? You heat it to an high temperature. The zinc at 800 degrees Celsius becomes liquid. And if you continue heating, the zinc evaporates. Please remember, it is not very easily said than done. It requires operations at very high temperatures. Still you can do it. Still this is a simple process. Not chemical processes are not involved. It is only physical process of heating, cooling, melting, solidifying, these things. So take zinc silver alloy, heat it, they become liquid, and further continuation of continue heating, the zinc distills off. It becomes vapors and distills off. Similarly, like your ether distills, benzene distills, zinc can also be distilled, and then collect the zinc separately. Whatever the remaining portion is nothing but pure silver. Okay, so what have we done? Using the Parkes process of desilverization of lead, all the silver in the lead we have extracted. Fine. But what happens? Please remember, in the distribution law tells that although it is 300 times more soluble in zinc, Still the lead layer will contain minute amount of silver, still it contains. So how to extract that? Then you have to take it to the next cycle of extraction. So continuous cycles of extraction, you can extract all the silver from the lead. Okay, so this is one of the applications of distribution law for metallurgy. Okay, fine. So I will stop here. In the next class, we are taking up one more application called solvent extraction. And that will be the end of this chapter called solutions.